Hello there and welcome to 10-Minute Physics. Today we'd like to take a look at Newton's second law. And I'd like to do this in under 10 minutes. And I'd like to just go through some of the nuances and aspects that are, I think, sometimes forgotten when they are taught in class. I think usually what happens is you are told this is Newton's second law. And you go, oh, that's it, that's the equation, boom, that's it. And maybe you don't really think about kind of the details of it and what it actually all really means. Let's take a look at the word definition. And it'll say the acceleration of an object is, as produced by net force, is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. So you could look at this and say, yeah, acceleration is directly proportional to the force. Acceleration is inversely proportional to the mass. And that kind of means if we were to put these two together, that, well, it doesn't kind of mean it, it actually means that, yeah, here. And then you would rearrange this equation. And you get, you know, F net equals, this is going to be a net force there, but it's F net equals ma. That's what that really means. That's what we have, you know. And you know that if you've got a constant mass, and if you were to say, hey, I want to have a very fast acceleration for this object, well, then I know I need to apply a very large force. So, and this goes into sports, right? If you want to kick a ball, throw a ball, do something like that, then, you know, and it's starting from rest, maybe like a break in pool, you know, the larger the force you apply, then the greater the acceleration it's going to have. Okay? Conversely, right, if the force is the thing that is constant, and you're only able to exert a certain amount of force, maybe this is more for like an engine or something which just has like a setting, right? You know, if that force is constant, you know that if you've got a very heavy object, the acceleration will be lower. If you've got a train, some sort of engine which is going to pull a certain number of cars, if you've got more cars attached, or even just one car with a heavier load in it, a bunch of iron ore compared to hauling a bunch of styrofoam, right? If you've got a higher mass, it will accelerate more slowly. Okay? Or the other way around, if the mass is quite low, then the acceleration will be much larger. So if you take out your golf club and you whack a golf ball, and your swing has a certain amount of force, the golf ball's mass, you know, is going to dictate, you know, what the acceleration will be. If you were to now put down like a, I don't know, like a cricket ball or a softball, like a baseball or something, and try out your golf club on that, same force, same swing, it'll be a heavier ball, and it'll have a slower acceleration. So these are inversely proportional. And I guess one thing that you can say, as I always tell my students, is, you know, when they say inversely proportional, the acceleration is inversely proportional to the mass. If you have two variables on the right side or the left side, on the same side of an equal sign being multiplied with one another, on the same side of the equal sign, there's an inversely proportional relationship. That means if this force or whatever other variables on the other side of the equal sign, if that's constant, then if one of these goes up, the other one goes down, and vice versa. If one goes down, the other one goes up. Okay, so I mean, this in a nutshell is what you get out of what you normally see in a classroom when they talk about this definition here. I feel this sorely kind of it doesn't sell really what Newton's second law is all about. Now, we can do a couple of other things. With the second law, we are saying F net is not 0. First law, the law of inertia, said, well, what happens when the net force is equal to 0? Here we're saying the net force is not equal to 0. What happens then? Well, then there's an acceleration. Okay, what will the acceleration be? Well, it's going to either depend upon the net force, because the acceleration is proportional to the force. We can also say the acceleration is inversely proportional to the object's mass. Okay, so, this, we've not really said anything different than what we were just talking about back here. But what I wanted to point out was first law, we are looking at what happens when the forces are balanced. Second law, we are looking at what happens when the forces are unbalanced. And that just gives a little bit more depth to this expression here. And then one final other thing that I'd like to say, since this really is the heart of what we're talking about with Newton's second law, is, and I'll go into this page so I get a little more room, you know that your acceleration is the rate of change of velocity, and therefore you can look at this. Well, wait a minute now. What this means is mass times, I'm gonna just write it a little bit differently. Okay, I'm gonna write it as F net is equal to the rate of change of momentum. This is a better definition for Newton's second law. This tends to be the definition, especially a while ago in older books, that they'll say, oh, this is the definition of a force. It's mass times acceleration. We don't really do that anymore. It's better to talk about it, your net force, as being the rate of change of momentum. This means so much more, and will lead us actually to the impulse change in momentum formula. We'll do that in another video. Okay, but this is a more effective way of thinking about it. Now, if mass is constant, and we were just talking about kicking a ball or pushing a cart or something like that, okay, then we can say, well, that if the mass is constant, we can write it out like this, and we can say, well, it's mass times this rate of change of velocity, and you're going to have, here you could have your v2 minus v1 over t. Okay, you could say that if mass is constant. If mass is not constant, well, then you have a little bit more of a complex situation. You'd have stuff, you got rocket equations, you've got your exhaust, you've got fuel being expended, and so the mass decreases. Maybe you are driving a dump truck full of gravel, and the stones or the sand or whatever keep falling off, and so that mass is slowly decreasing. Maybe you're flying a plane through like an icy kind of storm, and your propeller and your wings are accreting ice. Everything's kind of making things a little bit heavier. You do have situations where the mass will not be constant, and certainly in a relativistic case, mass increases as velocity increases. I would say for your high school physics, especially GCSE, we are not going to be concerned with these situations. I think we can pretty much always assume mass will be constant, and so you can have this expression here. But either way, both of these situations come from the fact that the net force is equal to the rate of change of momentum. Okay. I know I haven't said it here. Momentum is equal to mass times velocity. Maybe that's obvious from the context, maybe not. We'll go into a little more detail with this in a momentum video later on. But I hope that kind of gives you maybe a little more understanding than what is just typically said. Oh, here's the expression. Here's Newton's second law. It's just this equation. Yeah, we've got the proportionalities there. If you really wanted to, you could say, hey, rate of change of is it proportional to these? And in fact, because I've combined two proportional statements, this actually should be an equal sign, shouldn't it? And then you rearrange, and you get, rate of change. This is a rate of change of momentum, and I think that brings us back to what I was just saying here. This is probably a better representation of Newton's second law, okay? And that the net force that is exerted is going to produce a change in momentum of an object. So we'll see you in the momentum video. And I hope that that was good for you. If you've got any questions or comments, please leave them. Thanks for watching 10-Minute Physics. We'll see you next time.